This is the second lecture of the Semaphores chapter. After learning some basics in the use of semaphore, let's discuss a very influential and very important problem, the dining philosophers problem. This problem, originally called dining quintuple, later was called by Tony Hoare the dining philosophers. The dining philosophers problem was a problem in the final exam of a course taught by Dijkstra. This is the note written by Dijkstra. The version I presented is slightly different from the original version. Let me discuss the difference a bit later. Suppose we have a round table and 5 chairs. There are 5 philosophers in a thinking, eating cycle. That is, each philosopher thinks for a while. When he feels he's hungry, he just gets a chair. Then, at the middle of this round table, we have a very delicious spaghetti. In the original version, we have 5 forks. Each fork is between 2 chairs. A philosopher sits down, picks up his left fork, and then his right fork and eat. And if a chopsticks, a fork he wants is not available, he waits until that fork will become available. But as you may know, we don't need 2 forks to eat spaghetti. So in this presentation, I change the fork to chopstick. And the plate of spaghetti is changed to noodle. As many of you may know, it's nearly impossible to eat noodle with 1 chopstick. So it is more natural to use the chopsticks metaphor than the use of fork. So in this way, a philosopher sits down, picks up his left chopstick, and if it is available, if it is not, this philosopher waits. Once his left chopstick is taken, he tries to get his right. This philosopher can eat only if he has both chopsticks in hand. After eating, this philosopher puts down both chopsticks, assuming that both chopsticks would be cleaned magically. And then this philosopher leaves the chair. So let's quickly go through it. We have 5 chopsticks, each is between 2 chairs. A philosopher, when he feels hungry, he finds a seat, then tries to pick up his left chopsticks. If it is available, he uses it. Otherwise, he waits. After he is able to grab his left chopsticks, he tries to get his right. If his right is available, he gets it. Then this philosopher eats. After eating, he puts down both chopsticks and leaves, assuming that these chopsticks will be cleaned magically. If A philosopher, after gets his left chopsticks and the right one is not available, he waits until this right one will become available sometime later. So this problem is a very easily described problem, but to solve it properly, it requires some thinking. And this problem is also very influential, becoming the origin of several variants. We will discuss these variants later. So in the concurrent setting, let's assume that each philosopher is represented by a thread. Now, the chopsticks are shared item between two neighboring philosophers. Because each chopsticks is being shared by two, we need to guarantee each chopsticks can only be used by exactly one philosopher. Therefore, each philosopher must use a chopsticks in the critical section of that chopsticks. As a result, we need the semaphore to protect it. Remember, the first use of semaphore is for establish mutual exclusion. Therefore, each chopsticks must be associated with a semaphore with initial value 1. This initial value 1 actually states that at any time, only one thread can pass through the wait call of that semaphore. So a philosopher calls wait of that semaphore to pick up a chopsticks. After using it, that philosopher calls signal to release it. So this is a very simple idea. Then immediately, many of you may come up with this solution. We have an array of semaphore C, 5 elements with initial value 1 to each. So for philosopher I, he simply continues the thinking eating cycle. So this is the eating cycle. When this philosopher I wants to eat, he calls the weight of chopsticks I. We assume that chopsticks I is the left chopsticks of philosopher I. So philosopher I waits on his left chopsticks. And if his left chopsticks is being used by whom? By philosopher I's left neighbor as his right chopsticks. Philosopher I will be blocked by this wait call. Philosopher I could continue only if his left neighbor finishes eating and signal the semaphore CI. So after philosopher I is able to proceed, philosopher I must pick up his right chopsticks. His right chopsticks I plus 1 multiplies 5. So philosopher I, after picking up his left chopsticks, tries to pick up his right chopsticks. Of course, he may be blocked. If philosopher I is blocked here, it means philosopher I's right chopstick is being used by philosopher I plus 1 as his left chopsticks. So if philosopher I can pass this weight, it means philosopher I has already had both chopsticks I and I plus 1. Therefore, philosopher I can eat. After eating, philosopher I signals his right chopstick's semaphore, indicating allowing the next one to go. I'm done. Then philosopher I signal his left chopstick's semaphore, indicating I'm done. The next one could have it. So in this case, the blue frame indicates the critical section of the right chopsticks of philosopher I. That is chopstick I plus one. The yellow frame indicates the critical section of chopsticks I. Now, if you look at it carefully, you notice that the critical section of chopsticks I plus one is contained completely within the critical section of chopsticks I. But let me remind you, you may think that over after this lecture, the order of releasing chopsticks I and chopsticks I plus one actually doesn't matter. But here, for symmetric purpose, we always build a critical section so that a philosopher gets his right would release his right first. So the simple question is, does this solution work? I hope you could pause for a while and think whether this solution works. Intuitively, it works probably because a philosopher gets his left followed by his right and then eats. Logically, it looks a correct solution, but there is a big issue. Please think it over. From here, you're going to learn some headaches you may encounter in your programming assignment. Now, I hope you have figured it out. The issue is deadlock, because each philosopher is simulated by a thread. What if all five philosophers sit down at the same time and they pick up their left chopsticks at the same time, just like this? Every philosopher sits down at the same time. Every philosopher picks up his left chopsticks. Now, because we have only 5 chopsticks, if every philosopher picks up his left, there's no free chopsticks on the table available. Therefore, let's take a look at this philosopher. He has his left. He does not have his right, because his right is taken by his right neighbor as his left chopsticks. So every philosopher has something and waiting for something else. Unfortunately, that something else is being held by someone. And that someone essentially is in the same cycle. He has something and wait for something that is being held by someone else. So we have a circular waiting pattern. I am waiting for this one, which is being held by this one, and this philosopher is waiting for this one, which is being held by this one, and so on. And then the last philosopher has something and waiting for something else that is being held by the first philosopher. So circular waiting is a frequently seen pattern in a beginner's program when you use Semaphores. So we will explain circular waiting in great detail near the end of this course. So we know this solution looks quite easy and intuitive But we have a big problem. This big problem is deadlock. Now, if each philosopher is simulated by a thread, and if for some reason your system simply runs this 5 thread so that they all pick up their left chopsticks at the same time, then all threads will be in the waiting state, waiting for something to happen. But that something will never happen because the one who may cause that something to happen is also waiting. So this is a situation you have to avoid completely in your program, because in your program, the involved threads are all waiting. So how can we overcome this situation? If you look at this diagram, you know this circular waiting is caused by everyone does essentially the same thing. Everyone picks up his left and then followed by right. So how about this? We assign a philosopher who acts differently. That is, that philosopher picks up his right chopsticks first, followed by his left. Let me repeat. Let's pick a philosopher who acts differently. Here, differently means this philosopher, instead of picking up left followed by his right, this weirdo philosopher picks up his right first, followed by his left. Will this work? So let's investigate. Let's say we number the philosopher to be 0, 1, 2, 3, and 4. And the weirdo is 4. So the normal philosophers are 0, 2, 3. They always pick up their left, followed by their right. The weirdo, number 4, always picks up his right first, followed by his left. Here we use weirdo, but some other literature may refer to as lefty-righty solution. So here is the program. Now, because philosopher 4, the weirdo, acts differently, we have to write a piece of code which is different from those normal ones. So we have 2 versions of thread. Philosopher I, where I is 0, 1, 2, and 3. It follows the normal track. Wait for the left, wait for the right, each. And releases the right, release the left. But for the philosopher 4, the weirdo, wait for his right, wait for his left, it. Then releases left, releases right. So we have to write 2 thread functions, one for the normal, the other for the weirdo. So it's very easy to understand. We just switched the order of wait and also switched the order of signal. As I mentioned earlier, the order of signaling or releasing the chopsticks doesn't matter. So if you wish, you just change the order of these 2 to become this. But to keep the code as symmetric as possible, I will always use this version. Please think it over before you continue. Now, let's discuss this solution. You may have a hunch that the weirdo, because he acts differently, we may not have a deadlock. You are right. You are right. This weirdo or lefty-righty solution is deadlock-free. So how do we prove it? I prefer a proof by contradiction technique. Or you may do a constructive way. So let's assume that, always remember, normal philosophers pick up his left first, followed by his right. The weirdo picks up his right chopsticks, followed by his left. Now, let's assume that there is a deadlock. There is a deadlock. Then everyone has something waiting for something else. So let's study weirdo first. If all 5 philosophers cannot eat, it means they have only one chopstick and wait for the other. So if that is the case, if the weirdo cannot eat, the weirdo has his right without his left, right? And all the normal have their left without their right. But is this possible? If the weirdo has his right, so this normal philosopher won't be able to have these chopsticks. On the other hand, if the normal one has these chopsticks, the weirdo won't be able to have his right. So if this solution has a deadlock, that means both the weirdo and this philosopher would have this chopsticks, which is impossible because this chopsticks is mutually exclusive. Therefore, this cannot happen. The result is the circular waiting pattern cannot happen. This is proof by contradiction. But if you like a constructive or more algorithmic way, we still can start our discussion from the weirdo. The weirdo has 2 possibilities, whether the weirdo can eat or not. If everybody can eat, then there's no deadlock. Not necessarily everybody can eat because that's impossible. 5 chopsticks can only provide 2 philosophers to eat. So as long as one philosopher can eat, there is no deadlock. Hope you understand this. Now, let's assume that the weirdo has its right. Then this philosopher cannot have his left. Because this philosopher does not have the left, he cannot pick up his right. As a result, this philosopher's right neighbor could have his left. Now, if this philosopher can eat, there's no deadlock. Now, if this philosopher cannot eat, this means his right is being held by his right neighbor. Now, if his right neighbor can eat, it means this right neighbor has this one, and there's no deadlock. If this right neighbor cannot have this one, what does that mean? It means this one is being used by this one. Okay, therefore, in this chain of event, we assume that the weirdo has this one. So the weirdo and his left neighbor compete to get this free one. If the weirdo can get this one, the weirdo can eat, no deadlock. If the weirdo cannot have this one can be used by this philosopher. So this philosopher can eat. So no deadlock. Here, you can easily write an argument for that. Now, what if the weirdo could not have this right? So that means the weirdo cannot eat. Therefore, the weirdo cannot pick up his left. So the weirdo's left is being used by this one. You simply go through the same reasoning. If this one can eat, then this one has this one, this chopsticks. And if this weirdo cannot have this one, and go on, and eventually this one can have this chopsticks. So you could simply write a very simply write an if then else else if statement to complete this reasoning. So this is very algorithmic and constructive reasoning. It's more complex to explain, but most of you may be used to this kind of reasoning. On the other hand, the proof by contradiction is, if you are used to it, it's pretty simple. Let me go through it again. If we have a deadlock, then every philosopher has something, and at the same time waits for something to become available. So that means the weirdo has its right and this philosopher has its left, which is impossible because these chopsticks must be used in a mutually exclusive way. As a result, the weirdo cannot have his right, and his right neighbor cannot have his left at the same time. Therefore, the circulating pattern cannot happen. Then the proof is done. Isn't this simpler than a constructive proof? Well, you may disagree with me, which is normal. Actually, in mathematics, during the turn of the 20th century, the mathematical cycle as a community debated the usefulness of the proof by contradiction technique. Some mathematicians believe that to make mathematics useful, everything has to be constructive. So they rule out this proof by contradiction technique. This school is referred to as intuitionism, if I recall it correctly. But now, in the mathematics community, everyone accepted the proof by contradiction technique. So why don't you? Now, let's continue. There are several important questions here. The first one, we choose philosopher 4 to be the weirdo. Does this choice matter? Can we choose philosopher 2 to be the weirdo? I'm sure you know the answer instantly. The second question is, what if we have more than one weirdos? We have 1 or 2 weirdos, or 2 or 3, and so on. So if we have 2 weirdos, can this solution still be deadlock-free? It takes some thinking. Now, the third question for you to think about, how many weirdos can be there so that this solution is still deadlock-free? So this implies the answer of the second bullet. How many weirdos can be there so that this solution is still deadlock-free? The next question, can 4 or fewer philosophers cause a deadlock? That is, we only allow 4, 3, or 2, or even 1 philosopher to sit down. Can deadlock occur? We will use this concept for our next discussion, to the next discussion of the solution to this philosopher problem. Now, Notice here, this solution, the real solution is not symmetric because we write two pieces of code, one for the normals, the other for the weirdos. So that's usually a problem. As you know, for a beginner, writing one piece of thread, one piece code for a thread is already complex. Now, to break the circular weighting, you need to design a second type of thread. In other words, you're going to write the thread function of this weirdo type. For this version of Dining Philosophers, that's easy. But in reality, if the problem itself is already complex, writing a different piece of code could be complex or more sophisticated. As you know, more codes usually means more troubles. So this means we easily resolve the deadlock issue. But this is not good enough. This is not good enough. Of course, we could transform these two pieces of code and merge them into one piece. We will discuss this at the end of this lecture. Now, let's assume that all philosophers are normal. If all four philosophers, we only allow four philosophers to sit down, there will be an empty seat, right? We do not allow all five philosophers to sit down. We only allow four philosophers to sit down. Then there will be an empty seat. So the rightmost chopsticks, this one, which is the left chopsticks of this empty seat, is free. And this rightmost philosopher has a chance to use it. Let me quickly go through it. If this seat is free, nobody would use this one and this one. So this one can be used by this philosopher, which is usual, because this philosopher picks up this chopstick as his left. And now, because this philosopher is also free, the philosopher here is not allowed to sit down. This one is free. So what is the purpose of this chopstick? This is exactly the right chopsticks of this philosopher. Okay? So in this case, if every philosopher has its left chopstick, this philosopher would have two chopsticks and he can eat. Now, a simple exercise for you to think about, what if this philosopher cannot eat? What does that mean? Think about it. It's very easy. So if this philosopher cannot eat, can someone in this group of three eat? If you can answer this question quickly, then I'm sure you know the dining philosopher problem very well. Congratulations. And if you could not pick up the solution immediately, it does not mean you are not good. It just takes some time to think it over because you are not used to this kind of reasoning, which even though it's very easy, it still takes some time to get used to. In this solution, if we allow only four philosophers to sit down, the circular weighting pattern is broken and deadlock will never occur. So let's transform this observation to a program. That's pretty easy. Now, keep this in mind. We only allow four philosophers to sit down. How do we perform this? Remember, the second use of semaphore is a countdown lock. We set the initial value of semaphore to say k, then k thread or k calls to the wait method of that semaphore can go. The fifth will be blocked. Therefore, we could create a chair semaphore with initial value 4. In that case, 4 philosophers who cause the weight of the chair semaphore could go. The 5th philosopher who caused the chair's weight would be blocked. So here, we just put everything in the initial solution with deadlock here. Pick up the left, pick up the right. It, release the right, release the left. So this is what a philosopher does. Then we add the chair weight and chair signal here, because we are sure its initial value is 4. So only 4 can pass through. So only 4 philosophers can be here competing to get the chopsticks. And when a philosopher finishes eating, he simply calls chair.signal to release a chair, allowing the one who may be waiting here to get in. So this solution is interesting because it is symmetric. We need only one piece of code to finish the work. But we have an added cost. That is, we need one more semaphore, a counting down lock semaphore. So I hope you understand this solution, which is intuitive and simple to understand. The only thing you need to think over is the chair semaphore. Now, before we conclude this lecture, which is a very short one, I strongly encourage you to do these several simple exercises. We discussed the weirdo and 4-chair versions. Use execution sequences to show that some philosopher may have no chance to eat indefinitely. A typo here. In other words, this is referred to as starvation. A philosopher sits down, and he may never be able to get both chopsticks due to his left and the right neighbor compete against him. So use execution sequences to show that the weirdo solution could cause starvation. Some philosophers may not have a chance to eat. Do the same for the 4-chair versions. So this is your first exercises. Now the second exercise, suppose the chopsticks are numbered from 0 to 4. The chopsticks and the philosopher are also numbered 0 to 4. So a philosopher I requires chopsticks I and the chopstick I plus 1. A philosopher always picks up the low number chopsticks, followed by the high number 1. In other words, if the value of I is smaller than I plus 1, then philosopher I use I followed by I plus 1. If I plus 1 is smaller than I, remember this, there is a wrap around. So if philosopher I finds out I plus 1 is smaller than I, philosopher I picks up I plus 1. Compare this solution with the weirdo or the lefty-righty one. What do you find? Now, the third exercise. Suppose all chopsticks are in a tray rather than arranged between two. Each chopsticks is between two philosophers. All 5 chopsticks are in a tray at the middle of the table. A philosopher picks up a chopstick as his left. It doesn't matter which one. Followed by another as his right. Is this solution deadlock-free? And how about starvation? I hope you could use the syntax we used to develop a code for that. Okay, think about this. Is this solution deadlock-free? And is it starvation-free? And if it's not, use an execution sequence to illustrate at least one philosopher may have never had the chance to eat, even though he has a seat. Now, let's return to the original version. We assume that we ask each philosopher to do one more thing. A philosopher finds a seat and sits down, then flips a coin. If the result is a head, this philosopher picks up his left chopstick first. Otherwise, he picks up his right first. So we flip a coin to determine whether I need to pick up my left first or my right first. Is this version deadlock-free? Furthermore, is this version starvation-free? If it is not, use an execution sequence to illustrate that at least one philosopher could have no chance to eat. We will discuss more solutions from different point of view in later chapters and lectures. So this lecture is very short. I hope you like it. Our next lecture will be dedicated to some classical problems. The producer-consumer problem, originally referred to as the bounded buffer problem, also discussed in Dijkstra's seminal paper, which was prepared as a lecture notes. Then the reader's writer problem, followed by the roller coaster problem. So let me stop here. I hope you could watch this short lecture several times in order to understand the concept and at least 2 solutions, deadlock-free solutions, and understand how we can reach those deadlock-free solutions. And finally, please spend some time to do those exercises. So let me stop here and see you next time to discuss the classical problems. Goodbye.